Right, I'm going to go over some higher questions about light and the electromagnetic spectrum. These are all questions that have been used on past papers. This is part 1. There is a part 2, and both parts are worth about 40 marks. So there's quite a lot of marks traditionally asked by the examiners about light and the electromagnetic spectrum on your physics exams. Question 1. Radio waves from Jupiter take 40 minutes to reach the Earth. Light waves from the Sun take 8 minutes to reach the Earth. Calculate how many times further it is from Earth to Jupiter than from Earth to the Sun. State the property of electromagnetic radiation that is used in your answer. Right, the property of the electromagnetic radiation is all EM waves travel at the same speed in space. They all travel at the speed of light. What is the speed? It's 3 times 10 to the 8 meters per second. Right, so all we need to do is to compare as a ratio how many times will 8 fit into 40. 5 times. So Jupiter must be 5 times further away. Because radio waves and light waves travel at the same speed, and it took radio waves 5 times longer to reach the Earth. So Jupiter must be 5 times further away. Question 2. This question is about different types of electromagnetic radiation. The human eye can detect a range of wavelengths from violet at about 400 nanometers to red at about 700 nanometers. Figure 8 shows the relative sensitivity of the human eye to different wavelengths when inside a dark cave. Part 1. Use the information in figure 8 to determine the wavelength to which the eye is most sensitive inside the cave. Right, so that's the relative sensitivity up the side. So all we need to do is find where it's the highest, come down and see what wavelength that is. Right, so if that's 500, and that's 550, then you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means each box is 5. So I reckon that somewhere in between 1 and 2 boxes. So it's about 507 nanometers. Part 2. Calculate the frequency to which the wavelength corresponds. Give the unit. And it tells you that the speed of light in air is 3 times 10 to the 8. So it's in a cave and there's air, so that's the speed. So you need to know that the speed of an electromagnetic wave, which is what we call C, equals F times by lambda. So that's frequency times by wavelength. Now we need to rearrange that to get the frequency. So therefore, frequency equals C over lambda. Pop the numbers in. 3 times 10 to the 8 meters a second, divided by the wavelength, which was 507 was said. How do you know you've got to use that value there? Well, they haven't called it a new question, they've called it part 2. And part 2 is because it follows on from part 1. Frequency is measured in hertz, so we'll stick the units in straight away. And now we'll do the calculation. Remember that a nanometer equals times 10 to the minus 9. And that comes out as 5.26 times 10 to the 15 hertz. Now last year, I know that students needed to make sure they knew the difference between nanometers and micrometers. So actually you've got millimeters, which is times 10 to the minus 3. Then you've got micrometers, which is times 10 to the minus 6. And then your nanometers is times 10 to the minus 9. They've just made up some new prefixes, some new units. But at GCSE, these are the most common ones. Going the other way, you've got kilometres, so a kilo is times 10 to the 3. Then you've got a mega, which would be times 10 to the 6. And then you've got giga, which is times 10 to the 9. I don't know why I was putting metres on them all. You didn't need the metres. But we're only interested in the prefix. Using information from figure 8, describe how well the eye detects different colours of the visible spectrum inside the cave. So different colours, right. Now you might have forgot that they told you about violet and red. So basically, every one of these is going up by 50. So that there will be 650. And over here will be 700. So you've got the colour red is right over here. And remember your colours. Richard of York gave battle in vain. So violet is 400 nanometers. We just need to write the other colours in. So Richard of York gave battle in vain. So roughly spread out like that. And it's saying using information from figure 8. Describe how well the eye detects different colours. Right. Well, the eye is sensitive to blue and green. It's not so sensitive to violet and indigo, or yellow, orange, definitely not red. So that's worth 3 marks. So we'll just write down what I've just said. And just to back it up, we'll just pop some wavelengths in, just in case. So yellow, orange and red, that goes from like 600 nanometers up to the 700 nanometers. Violet and indigo, so you're looking at like 400 up to sort of 450. And we're sort of seeing the blue and the green is round about the 450 up to sort of 550. Question 3. Radio waves and gamma radiation are at opposite ends of the electromagnetic spectrum. Compare how these two electromagnetic radiations are produced. Right, well, let's start with radio waves. Now, basically, humans can produce radio waves in aerials by making free electrons oscillate. And that's what we call alternating current. Right, so I've already got 4 good things down there. So if we can say at least a couple of things to do with gamma rays, then we should be good. So basically, gamma rays are given off randomly when the nucleus of a radioactive isotope rearranges to make itself more stable and gives off energy. That energy is basically gamma rays. Or you could say they're given off during nuclear fission or fusion. But you only really learn about that in triple. Right, so you'll easily get 6 marks for that. Question 4. Figure 3 shows an image taken at night using a camera that is sensitive to infrared radiation. Well, that's just a posh word for heat. Radiation with shorter wavelengths shows as a brighter area in this image. Shorter wavelengths, brighter. Explain why the people can be seen against the background of this image. Right, well, if the people can be seen, they've just told us the answer. These people must be given off infrared radiation, which is a shorter wavelength. So infrared radiation has a shorter wavelength than the wavelength from the background. They said it themselves. Shorter wavelengths appear brighter, and it's got a shorter wavelength. Question 5. Ultraviolet waves cover a range of frequencies. Scientists divide the range into 3 types: UVA, UVB and UVC. The table in figure 14 shows the frequency range for each type. So UVA, UVB, UVC, and there's the ranges there. So 7.5 times 10 to the 14 to 9.4, 9.4 times 10 to the 14 to 10 times 10 to the 14, and 10 times 10 to the 14 to 30 times 10 to the 14. So the frequency is low, medium, and high. Figure 15 is a diagram about the effect that the Earth's atmosphere has on 3 types of ultraviolet radiation: UVA, UVB and UVC. So the same as what they were saying up the top. Right, there's the Earth's atmosphere, and you can see how much is passing through or not. Describe how the effects change with wavelength. Oof! So they've given you all the information to do with frequency, and now they turn around and ask about wavelength. Well, I've seen this question a few times, so I knew that was coming. Using information from figure 14 and 15, so we need to talk about the wavelength. The width of the arrow drawn indicates the amount of radiation that is involved. Calculations are not required. Right, well, let's convert the frequency into wavelength. Now, if these are all ultraviolet waves, that means that they all travel at the speed of light in a vacuum, 3 times 10 to the 8. So C equals F times by lambda. So frequency times by wavelength. Now, the thing is if this number is a constant, as the frequency gets higher and higher, it must mean that the wavelength gets lower and lower. So if you've got a little frequency, right, if that number's little, it must mean that this number's big. So you must have a long wavelength. If this frequency is medium, it must mean that the wavelength's medium. And if the frequency is high, so if this number here gets bigger, it must mean that this number here, the wavelength, gets smaller. So that just must be a short wavelength. Remember, frequency times by wavelength equals the speed of light. Right, so it wants us to talk about the wavelength. Right, so UVA has got a long wavelength, UVB got a medium wavelength, and UVC has got a short wavelength. So when it's a long wavelength, you get a lot of UVA transmitted through the Earth's atmosphere. UVB, only a little bit is transmitted through the Earth's atmosphere. and UVC with a short wavelength, none is transmitted and some is reflected. We might get 4 marks for that, but just to make sure, let's see what the trend is. So as the wavelength gets longer, you end up getting more being transmitted through the Earth's atmosphere. Or you could have said the opposite. The shorter it is, the less that gets transmitted. Now, if you didn't want to get fixated on the transmission, you could have said absorbed. So not much gets absorbed with UVA. Most is absorbed with UVB. And let's say with UVC, it's mostly absorbed as well. So you might have to practice shortening that answer. Question 6. A student investigates how the angle of refraction varies with the angle of incidence when light enters a glass block. There we go. Describe how the student should perform this investigation. 4 marks. Right, so they're going to shine the light in and they need to measure the angle of incidence. So the angle of incidence is the angle between the ray and the normal. So they're going to need to measure that. Now, if you've saw one of my other videos, I like to use the acronym FAST. If the wave travels faster, it's going to move away, and if it moves slower, it's going to move toward the normal. Right, so if the light just came straight, it would go there, but it's not. It's going to slow down. As light goes into glass, glass is more dense, so light slows down. So the light is going to bend in toward the normal. How far in? Doesn't matter. Just don't bend it right down. So that's where it would go if it didn't bend, and it's going to bend in towards the normal. So that's lovely there. And we need to measure that angle there, R. It wants us to investigate how the angle of refraction varies with the angle of incidence. So we're obviously going to have to measure the angle of refraction. And that angle is between the refracted ray and the normal. So I guess I need to go back up here where it says measure the angle of incidence between that should say incident ray and the normal. That's the incident ray. And this here will be the refracted ray. You could write it on the diagram if you wanted. And then because it says varies, we'd better repeat that for different angles of I. Question 7. Microwaves are used to send and receive television signals from high orbit geostationary satellites. Describe why microwaves rather than radio waves are used. Right. Radio waves can't penetrate through the ionosphere, which is an upper layer of the Earth's atmosphere, and they wouldn't reach the satellite. If you're wondering why, it's because the radio waves have got a long wavelength, so microwaves have got a slightly shorter wavelength, it's slightly more energy, and they can penetrate through the ionosphere okay. The International Space Station, ISS, has several solar panels called wings. The wings convert energy from the sun into a form useful in the ISS. Which description below describes a light wave? So light waves, yet they're basically transverse waves and they are electromagnetic. Now I can't believe that it hasn't asked us for the electromagnetic spectrum yet. You've got light in the middle. So that's Richard of York gave battle in vain. So if violet's here, that means that ultraviolet's there. Red's there, that means that infrared is there. Ref for red, ref for radio, which is the longest. The shortest is your gamma. Next to that is X-rays, which are pretty short. And the only one that's missing is microwaves. Just in case you wanted to know. I don't know why I did that. Part B. In 1 second, the useful energy available from one wing is 34.3 kilojoules. So that's the useful energy. The energy incident on the wing, so that means the energy sort of landing on the wing from the sun, is 5 times this amount. What's the percentage efficiency? Right. Well, percentage efficiency equals the useful energy out divided by the total energy in multiplied by 100. Right, so the useful energy was 34.3 kilojoules. The total energy in was 34.3 times by 5 because it said it was 5 times the amount. Multiply all that by 100 and that's 20%. Well, I mean, it was always going to be 20%, wasn't it? Because the total amount of energy landing on it was 5 times the amount, which meant that only 1/5 of the total amount of energy was actually being used in a useful way. And 1/5 as a percentage is 20%. Part C. A wing is in direct sunlight. The ISS is not receiving energy from the wing. The temperature of the wing remains constant. Oh, I can see where this is going. I've seen this before. Explain why the temperature of the wing remains constant in these conditions. Right. Well, it must be because the amount of heat that you are losing equals the amount of heat that you are gaining. That's why your temperature would remain constant. Question 9. Figure 8 shows how a glass prism is used to produce a spectrum from a beam of sunlight. So remember, a spectrum is your colours. Richard of York gave battle in vain. Explain in terms of refraction and wavelength the paths taken by the light through the prism. Right, well, we've already saw a question before. We know that red's got a long wavelength. It said it was 600 nanometers, and it said that violet was only 400 nanometers. You're supposed to know that red's the longest anyway. Now, red has got a long wavelength, and it's being refracted the least. Okay, it's being bent down the least. And violet light has got the shortest wavelength, and that is being bent the most. So, refraction and wavelength. And don't forget the fact that what we're seeing here is white light being split up into the different colours. Basically, the relationship is the longer the wavelength, the smaller the refraction. Run out of room a bit there. Part 2. Describe how a student could develop the procedure shown in Figure 8 to search for evidence that sunlight consists of additional electromagnetic waves with frequencies lower than visible light. Right, well look, do you know that picture I showed you before? So what we've just looked at there is light, right? Richard of York gave battle in vain. Now, if we're looking for electromagnetic waves with frequencies lower than visible light, right, over here the wavelength is long, and that means it's got a low frequency. So what we're looking for really is evidence that infrared exists. I've seen this question loads of times. That's how I know what to do. And by you watching this video, now you know what to do. So the only electromagnetic waves we can see are the colours. So it looks like there's nothing here, but actually there is. This is where you'll find infrared. I mean, down here is where you'd find ultraviolet as well, okay? But they're not interested in the waves with a high frequency. They're only interested in these waves over here with low frequency. Now, what did I tell you before? Infrared is just a posh word for heat. So if we take a thermometer and place a thermometer here, then the thermometer should get hot, right? The temperature of the thermometer should increase, and that'll mean that infrared, although we can't see it, it's definitely there because we're using the thermometer to detect the heating effect of the infrared. Now, how do we say that? Because I've been a bit waffly with this video, I'll be honest. So place a thermometer beyond the red light. The temperature should increase. And that's proven that infrared is there. So that's evidence that the sunlight consists of additional frequencies. Lower frequency than visible light. I'm trying to use as much of the question in my answer, because then you know that you're using the right words, don't you? And finally, number 10. Some television remote controls use infrared radiation and other remote controls use radio waves. So infrared has got a shorter wavelength and radio waves has got the longest wavelength. Explain why an infrared remote control may not switch on the television from behind an armchair, but radio wave remote control always will. Right, well, we could just take a punt and use our common sense. If the TV's there and your armchair's there and you're trying to zap the telly from behind the chair, well, infrared mustn't go through the chair, but radio wave must. Simple as that. And there we go. I'll be honest, you probably only needed to put either that or that. You didn't need to talk about both. But make sure that you are talking about the wavelength and whether it gets absorbed or not. Okay, wavelength transmitted in that case. Alright, and there we go. There's 40 marks. Boom. Good luck in your exams. Keep practicing. I'm going to keep bashing these papers out. The more that you practice, the better you get. Simple as that. Work hard, be nice, and bye for now.